Draw this here. So it is VDC. So it is induction motor. So you have from the three-phase bridge inverter, you have the three-phase supply. So you give the numbering of the switches as well, like 5, 6. Okay. So from the DC you convert into AC using this bridge inverter, and based on that we will get that. Okay. So now you see here. So if you recall the bridge inverter, what is the output you will get here? Means this we have done already. I told you already that this we have studied in the power electronic course, the operation of this bridge inverter. So I am not going to explain once again here. So let me take this 120-degree conduction. So if you take the 120-degree conduction, then the output voltage waveform, line to line voltage waveform we will see here, VL. This voltage waveform I will just show you now what we got in the previous semester. So just revise that part, then you will understand yourself. So this is 5 by 6. This is 5 pi by 6. Okay. So it means the duration of this is 120 degrees. Okay. So for this case, now it is a non-sinusoidal waveform. So as it is a non-sinusoidal waveform, so you generally, okay, the expression for the line to line voltage, or the expression for the line voltage of this inverter that is going to the induction motor stator, okay, can be represented with an expression. So as it is non-sinusoidal waveform, so you have to find out the expression in terms of the harmonic Fourier series. Using Fourier series, you will get that. So line voltage VL is equal. I'm writing this directly because we have done this analysis in the past. 1, 3, 5, and so on to infinite. 4 VD by N5 cos 5 by 6. So N, what is N? Cos N by 6 into sine omega t plus 5 by 6. This is the expression you will get when you resolve this waveform into a sum of sinusoidal waveform using Fourier series. So you will get this thing. So now what you will do here is that when you do the simplification of this further, you got here N5. Now this corrections are there here. N5. Okay, so now there is one more N here. N is also there. So cos N5 by 6 into sine N into omega t plus 5 by 6. This is the expression for the voltage. So then, if you expand this expression, VL is equal, what you will get here is that 4 VD by 5, 4 VD by 5, 4 VD by 5, and so we will take n is equal to 1 first, then cos pi by 6 into sine omega t plus pi by 6. Now we will take n is equal to 3, then 4 VD by 3 pi, 4 VD by 3 pi, cos 3 pi by 6 into sine 3 into omega t plus pi by 6. This you will see, and so on. And so on. So now when you do the simplification of this, okay, because cos pi by 6, you know it is root 3 by 2. So if you do the simplification of this, what you will get the answer is that, I will write the answer here directly. Okay, so VL is equal to root 3 by 5 into VD sin omega t minus 1 by 5 sin 5 omega t minus 1 by 7 sin 7 omega t, and so on. Okay, so this you will get as the line to line voltage. Okay, for example, if you want to find out the phase voltage, what do you do? So your line voltage divided by root 3. So then you substitute in that, you will get that answer. So this is phase voltage. So this is phase voltage. So you will get here 2 VD by 5 into sin omega t minus 1 by 5 sin pi omega t minus 1 by sin 7 omega t, and so on. This you will find out the expression. Now you see here the phase voltage depends on VD. Means the voltage, either the phase voltage or the line voltage, it is proportional to VD. What is VD here? VD is nothing but VDC. Okay, I think I put VD here. So this is VD. So VD is the supply voltage, DC voltage. So you want to get different value of VP, that is, you want to get different values of the voltages to your induction motor. So you vary the value of VD. There is a logic here. Okay, now how do you vary this? How do you vary this? See here, logic, we have understood this thing, right? What is the logic here? The output voltage of the inverter depends upon the input voltage. Mathematically, you have seen this thing. So you want to change output voltage of the inverter. Why do you want to change output voltage of the inverter? Because you want to vary the speed and torque of the induction motor. So definitely you need to change this supply voltage to the induction motor. So to change the supply voltage, what is the clue here we got is that by changing the DC voltage, that is VD, we can change the output of the inverter. So a simple thing. Then how do you do that? So what is the logic behind this? So how do you implement this? One way is using a chopper. Run circuit here. This is a DC supply. This is the DC supply. Okay. Then you have the inverter here. We have the inverter here. Then you have the inverter here. Then the output of the inverter goes to the induction motor. So you see here now, so you will get the DC supply to the inverter, then the inverter will convert the DC to AC, and that goes like this. What we have seen here, the output voltage of the inverter depends on the input DC voltage. It means the voltage of the input to your inverter. So if we can vary the input DC voltage, then we can vary the output voltage also. So how can I vary this is that using a chopper. So we call the chopper. What is a chopper? It does. So a chopper, so your DC, a chopper is there. Then I hope you remember this thing that a chopper will convert one DC value to another DC value. So by controlling the chopper, the input voltage, that is VD, this is VD. The voltage here is VD. So this VD will vary by controlling the chopper. So if VD is varying, then V phase also varying. So you can get like that. Say for example, you don't have a chopper. Then in another words also we can see this thing that you have the inverter here. Then using induction motor, and then assume that you have a three-phase supply. This is the three-phase supply. So you have the rectifier here. This three-phase rectifier is there here. And now, of course, you will have the control rectifier. Remember now. Why control rectifier? Because if it is control rectifier, by controlling the firing angle, you can control the output of the converter, output of the rectifier. So different VD you will get here. This is another way to get different values of VD. Okay, to the input of the inverter. Now you have another type of inverter. That inverter we call it as PWM inverter. So what is this PWM inverter? Is that you will use the pulse width modulation technique. Okay. So what is the pulse width modulation technique? You have the reference signal and you have the carrier signal. So I hope you remember this thing that the reference signal is a sawtooth waveform. Whereas the carrier signal may be a DC or maybe a sinusoidal waveform also. So it depends upon whether it is a just PWM or sinusoidal PWM. It depends upon that. So for example, if I take the sinusoidal PWM, then what is the carrier waveform? You will get the carrier waveform will be something like this. So this black color one, this is reference, whereas this red color one, it is the carrier waveform. I hope you know how to get the pulses here. That by comparing both the waveforms, you will get that. For example, if it is more, okay, so something will get the output like this here. Okay, so if the carrier waveform is more than, it means here it is more. You see, here it is more. The red color waveform is above the black color. In that case, it is high. Now, otherwise, it is low. So here once again low. Then I hope we have discussed this already in previous courses itself. By comparing this, you will get the pulses. So these pulses will go to the switches of the PWM inverter. Okay. So what is a PWM inverter? I will draw here that this is your PWM inverter. This is PWM inverter. So either you will get the DC supply directly, that is one way. The other way is that you may get the DC supply from a rectifier also. Okay, instead of having this DC supply directly, this is DC supply. So in this place you may have a diode rectifier. Now remember, now I have taken the diode rectifier, not this thyristor rectifier, because already you are controlling in the PWM inverter here, so you don't need a thyristor rectifier here. And then PWM inverter. This is induction motor. So here you have three-phase supply. This is another type of PWM inverter. It depends upon how you are getting the DC supply. Whether you are getting the DC supply directly or you are getting from the output of a rectifier. Depends upon that a small slight modification will be there. So now you know very well that how do you see this reference waveform is fixed one. What is the variable one here? Carrier waveform is the variable here. So, so when the carrier waveform is varying, the pulses here varies. When the pulses here varies, the output also varies. That's it. So this way you can control the induction motor. Okay. So it depends upon the carrier waveform, the magnitude of the carrier waveform. So it is represented by one index. That index we call it as modulation index. Modulation index here. What is it represents is that it is ratio of so it is the ratio of so it is the ratio of amplitude of carrier signal divided by I'll write somewhere else here. I will write here the modulation index. So modulation index M is equal amplitude of carrier signal divided by amplitude of reference signal. Okay, so now the amplitude of the reference signal is always constant. That is this reference waveform, black color waveform, that is fixed always. So we can say this thing that M is proportional to amplitude of carrier signal because the denominator is a fixed one. So we can write directly like this equation. Okay. So this way we control the modulation index. Okay. Then we can easily control the output of the inverter. Okay. The next one is that how do you get this braking and multi-quadrant, that is four quadrant operation in induction motor that we will examine now. So here I hope you remember what is the braking here. Okay. So so what happens in the braking? I hope you remember now. Okay, it depends upon two types of. Okay, we'll discuss the two types of braking. Of course, three types of brakings are there. The most important here are only two types that we will discuss. One is dynamic braking. Dynamic braking. So in this method of dynamic braking, let me draw uh, an equivalent circuit here. The block diagram I will draw, then I will explain. This is PWM inverter that goes to the induction motor. So here you have another switch one. Then here you have the diode bridge. This is your diode bridge. Then here you have the supply, three-phase supply. You see the operation here. The operation is very simple here. So you see the operation here. Here you have two switches. Here you have two switches. So here you have two switches, switch one and two. Okay, so whenever you want to, for example, if it is operating as a motor. So if it is operating as a motor, switch one is closed for motoring. For motoring, switch one is closed. So this three phase, three phase DC supply. Okay. Now two is open. Switch one is closed and switch two is open. Okay. For what? For motoring. For motoring, switch one is closed, switch two is open. So when the switch is closed here, what do you find out? This three phase supply after the rectification will go to the capacitor here because this is open, so it will directly go to the capacitor. So this DC will be converted into AC. Okay, this DC will be converted into AC using the PWM inverter. So this operation takes place. So the supply is going from source to the load. That's motoring. Now for the braking condition, what you do is that for the braking condition, you open switch one. Switch one is open. For the braking condition, switch one is open. Okay. So when the switch one is open, now already two is also open. So what do you find out here is that you will make the frequency of this converter, this inverter, you reduce the frequency of this inverter. So you reduce the sense part. I hope this PWM inverter, it gives AC, and AC has some voltage and frequency. By controlling the PWM inverter, you can control the voltage and also you can control the frequency. Say for example, I reduce the frequency. Say for example, so when I reduce the frequency, what will happen if I reduce the frequency? When F is reduced, okay, then your N also gets reduced. Okay, which N? The Ns synchronous speed is equal to 120 F by P. So your Ns will get reduced. Please see here. So your Ns will get reduced. So when the Ns gets reduced, what about Nr? Nr cannot get reduced immediately because of the inertia of the induction motor. Nr cannot be reduced immediately, but Ns can be reduced immediately because Ns is the synchronous speed. It depends upon the frequency. Now you reduce the frequency. How you are reducing the frequency? By controlling the PWM inverter, you reduce the frequency. Once the frequency is reduced, so the synchronous speed gets reduced. So once the synchronous speed gets reduced, what is the S value? S is equal to slip. Slip is equal to Ns minus Nr by Ns. So here in this case, you are reducing Ns value. When you reduce the Ns value, for example, if you reduce the Ns value below the value of Nr, then S becomes negative. S is negative now. If S is negative, then you will see yourself the voltage is negative, okay, and it has some consequences. So when it has some consequences, what do you expect? What will happen there is that it acts as a generator. It simply acts as a generator. So what is the logic? I hope you remember this thing even in case of the induction motors also, that when you reduce the synchronous speed below the rotor speed, or if the rotor speed is more than the synchronous speed, see here. So in both the cases, the rotor speed is more than the synchronous speed. So if you achieve that, then we have seen ourselves this thing that the motor will work as a generator. Okay. So how do you explain that mathematically? Is that when it is less than Nr, then S becomes negative. So if S becomes negative, then the power also becomes negative. See, power positive in the sense the power is going from source to the load. If power is negative, then the power is going from load to the source. Okay, that's important. So it is going from load to the source. In the opposite direction it will go. So when it is going in the opposite direction, then what is the status here now? See, you have opened the switch. Why you have opened the switch? Because you want to enter into braking condition. So you, whenever you want to enter into braking condition, first you open the switch number one. When you open the switch number one, what do you find out is that this rectifier and AC part is totally disconnected, and you reduce the frequency of the inverter. Then the synchronous speed will be reduced below rotor speed. Then the slip becomes negative, so the power becomes negative. So P becomes negative. So when P becomes negative, then the power is flowing from induction motor to the source. Here, what is the source here? The capacitor is the source here. Why the capacitor is source here? Because this is totally disconnected. So only capacitor is left here. So the capacitor will get charged. So the power comes like this, and capacitor will get charged. So when the capacitor is getting charged, its voltage will increase. When its voltage is increased, and when its voltage is increased beyond a set value, for example, this is capacitor voltage. So when VC, so because of that, VC will increase. See, simple logic here, that you reduce the frequency, you reduce the frequency, so ns will get reduced. If ns gets reduced, s becomes negative. If s becomes negative, power becomes negative. Then the power flow from the induction motor to the capacitor, so the capacitor voltage will increase. If the capacitor voltage, which is increasing here, if it is more than the set value, a value will be set for the capacitor. So if it is more than the set value, then you close switch number 2. So switch 2 is closed. When you close the switch, when the capacitor voltage which is getting charged here, or which is increasing here, when the capacitor voltage which is increasing here, if it is reaching beyond a set value, then you close the switch number 2. So when you close the switch number 2, what do you expect here? One is open, whereas 2 is closed. So switch 2 is closed now. So you don't close immediately. You will close only when the capacitor voltage is more than the set value. So when you close the switch here. So when you close the switch here, what do you expect now? You will expect that the energy which has come from the induction motor to the capacitor, that energy will be dissipated through the resistor. So this happens. So indirectly we can say the energy which is stored in the induction motor is dissipating in the resistor as heat, because you have opened the switch number 1. So this is called dynamic braking. So when you do this, what will happen now? When you do this here, the energy, the induction motor loses energy. So when the induction motor loses energy, its speed decreases. Okay, so that's called dynamic braking. I hope you have seen this dynamic braking even in case of the DC machines also. There also you recall there is a resistor is connected across the source, or across the motor you connect a resistor. Here also we have connected a resistor across the motor, and that resistor will dissipate the energy which is coming from the motor. So that is called dynamic braking. Here also same thing is there, but here you have two switches. So only thing is that which switch is on and which switch is off. For motoring condition, which one is on, which one is off. For braking condition also, which one is open, which one is closed. This you know, and at the same time you have to remember this thing, that the frequency gets reduced here. Okay, this is dynamic braking. Now you have another type of braking. I hope you know this thing, that is the regenerative braking. So in the regenerative braking, I will just draw the circuit diagram of the regenerative braking. You will see the diagram of regenerative braking here. Please see this here. So we'll start from the end here. There is an induction motor here. Then you get the supply. Remember, always you always get the supply from the inverter, and that too it is a PWM inverter. So you draw the PWM inverter. Now it is inverter number 2. There is another inverter number 1 is there, that we will draw. Then you have, because you need a DC, you need a DC to your inverter. So that DC is here in the capacitor. Okay, that's the reason you need a capacitor, and inductor is that to filter that. Then you have PWM inverter 1. And then, so, in the regenerative braking, what we will do is, that we will, 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 Okay, so uh, then here we have three-phase supply. This is Ix source current. Okay, so source current. Okay, and the voltage here is source voltage. Then I will tell you this one, this part, this extra part which you got here. Okay, it has a name. It has a name here. You can call that as it is called SLC. SLC in the sense synchronous link converter. So here you give the pulses here to the inverter number 1 from the controller. Plus minus. And here you have 3 DC reference. This. Then the error goes here. So this is a block diagram. So I will explain now the block diagram here. So this is regenerative braking. So I told you already, you might have remembered this thing, that regenerative braking in the sense, what is this regenerative braking is that the energy which is stored in the induction motor, the energy which is stored in the induction motor, it will go into the source. Unlike in the dynamic braking, the energy which was there in the induction motor during braking process, it will be dissipated. It will be dissipated as heat in the resistor, which you have seen just now. Whereas in case of the regenerative braking, the energy which you collect from the induction motor will go directly to the source. Will go directly to the source. This is the source. So this is the source voltage. So directly goes to the source. Or you are collecting back the power from the induction motor. That's called regenerative braking. Okay. So now in the case of the induction motor, you need the help of a synchronous link converter for the uh, proper functioning of the reason. What is the purpose of this? Now even without the synchronous link converter also, you can take the energy from the induction motor. Okay, that is there already. Even you have studied in case of the DC motor also, that without the synchronous link converter also we can perform this. But now what is the advantage of this SLC, synchronous link converter? What is the advantage of this is that this converter, now when you collect this, see, when you collect the power back from your, how do you do that? Same thing, that you reduce the frequency here, you reduce the frequency of the supply, then the slip becomes negative, so the power becomes negative. So you will find out the power fed back, it means the current is coming backwards here like this. When the current is coming backwards, now when you draw the waveform of that current waveform will be a non-sinusoidal waveform. That current waveform will be a non-sinusoidal. It may be of any shape. It depends upon some other components present in the converter. So it is a non-sinusoidal. So when it is non-sinusoidal, the current IS is also non-sinusoidal. So when it is non-sinusoidal, then what do you find out now? The source voltage is sinusoidal, whereas the current is a non-sinusoidal one. So you know that there will be definitely harmonics. So because of this harmonics, some more problems will arise. What this synchronous link converter does is that it modifies this non sinusoidal current into a sinusoidal current. That's the main agenda of this synchronous link converter. So without the synchronous link converter also, the induction motor will give the power back to the source. But in that case, what is the problem you face is that the current, that is the input current, is a non-sinusoidal one. So if the current is a non-sinusoidal one, then there will be lot of harmonics. So, and you know very well what are the problems associated with the harmonics. So now to avoid this, we are using a synchronous link converter here. What is a synchronous link converter? It is a combination of the inductors. It is a combination of the inductors in series with the PWM inverter. So you have an extra PWM inverter in series with this inductor. So when you join like this and you take the sufficient value of L, so that what you find out is that the current Is will be a near sinusoidal. So if it is a sinusoidal, then supply voltage is also sinusoidal, Is is also sinusoidal. So there won't be any harmonics at all. Maybe there is a phase difference. Okay, that really does not matter to us. Only thing is that the current waveform should not be a non-sinusoidal waveform. So if you follow this procedure, then the synchronous link converter will modify the current into a sinusoidal waveform. So here two things we are achieving. One is we are collecting the power. At the same time, the harmonic problem also rectified using the synchronous link converter. Okay. Now here what do you find out the here closed path? Now same thing. Closed path is that you will sense the DC voltage here. Then you have the reference DC voltage. Then based upon that the error, then the controller. Based upon that they will get the pulses. Based upon that they will get the pulses. So you always so it's simple thing that you set here the voltage, you set the voltage here, whichever the voltage you set, it will be compared here, and based upon that it will control the PW inverter number 1. So this is the regenerative braking of that. Now in the reason, now see how do you operate the multi-quadrant operation. The other topic is there, multi-quadrant operation. So multi-quadrant operation means, so you will operate in all the 4 quadrants. That's it. So how do you operate in the all the 4 quadrants? Okay, this is torque, this is speed, minus t minus omega. So how do you do that? We have seen in case of the choppers how we can operate, or how we can operate the DC motor in all the 4 quadrants. We know very well this is motoring, forward motoring, and this is forward braking. This is a reverse braking. Sorry, it's not reverse braking, it is reverse motoring. Reverse motoring. Whereas this is a reverse braking. Okay. So forward motoring, forward braking, reverse motoring, reverse braking. So what is the logic here? How do you enter into braking? Just now we have seen this thing that you reduce the frequency of the supply that is going to the induction motor, then slip becomes negative, so power becomes negative. Okay, so it will enter into forward braking. But now you see in first quadrant and second quadrant the speed is positive. The first quadrant, second quadrant speed is positive, but the torque may be positive, torque may be negative. Okay, that is forward motoring, forward braking. Now the third and fourth quadrant, same thing will do, but except you reverse the speed here. So now I hope you know what is meant by reversing the speed. Reversing the speed in the sense the motor runs in the opposite direction. I hope you know how can we make the motor, induction motor, that is a three-phase induction motor, to run in reverse direction. One way is that you change the phase sequence. Now here, say for example, it is R, it is Y, it is B. Say for example, then what you do is that this R terminal you connect to Y, okay, R you connect R, you do one thing, both R and B you interchange. So you bring R to B and connect B to R. So change the phase sequence. I hope I don't need to explain much about this, about change phase sequence. Okay, I hope you know how to change it. Just interchange terminals, interchange R and B. That's it. So change phase sequence. So if you change the phase sequence, I hope you might have studied in the induction motor that how do you reverse the direction of the induction motor, of a three-phase induction motor, by changing the phase sequence. By reversing the phase sequence, the rotation also gets reversed. So if it gets reversed, it enters into negative speed. So it enters into third and fourth quadrant. Once again, a third quadrant, it is motoring. So in the motoring condition, the supply comes from the source to the load. Once again, in the braking condition, what you do now, you reduce the frequency. Then once again, the slip becomes the slip becomes the slip becomes negative. So the power becomes negative. Then everything will be okay, done. So now you see, I will just repeat this multi-quadrant operations. What is this multi-quadrant operation? Is that you have four quadrants: one, two, three, four. So one and two, you see the speed is positive. So when the speed is positive, then you don't do any kind of changes to the phase sequence. You don't do any kind of changes to the phase sequence. So then the power comes from the source directly to the induction motor. That is the first quadrant. In the second quadrant, what you do is that in the second quadrant you reduce the frequency, so that the speed becomes negative, power becomes negative. So the power flows from induction motor to the source. This happens. Now third and fourth quadrants, before you go to the third and fourth quadrants, what is the situation you find out in third and fourth quadrants? The speed is negative. So if the speed is negative, I hope you know how to reverse the direction of the induction motor. For the three-phase induction motor, to reverse the rotor direction, you reverse the phase sequence. So this is RYB. So you reverse the phase sequence. That is, you make it as RBY. RYB, you make it as RBY. So when you just interchange any two phases, then it becomes a reversed phase sequence. When the phase sequence is reversed, obviously the speed is in the reverse direction. That is, the motor runs in the reverse direction. So the omega becomes now minus omega. So it means either now you can operate in the third quadrant or you can operate in the fourth quadrant. If it is in third quadrant, same thing. You don't do anything except reversing the phase sequence. Then the power comes from the source to the load. Whereas you see here, when you, it depends you here. The third quadrant, torque is also negative, omega is also negative. So omega is negative in the, that is sorry, speed omega. Yeah, omega is negative in the sense you reverse the phase sequence. Omega is positive in the sense you don't change the phase sequence. When do you have torque positive? Torque positive in the sense you don't do any kind of alterations. Directly source will go to the source, will give power to the load. Whereas when you want to make torque negative, then you reduce the frequency. So I will write here omega positive. It means positive phase sequence. Positive positive phase sequence in the sense RYB you take it as. Omega negative in the sense negative phase sequence. You reverse the phase sequence. Then fourth one, the third one is torque is positive. Say for example, torque is positive in the sense, what do you do whenever you want to have positive torque? That Ns greater than Nr. Okay, N is greater than Nr. So you have to do like this. Whereas when you want to have torque negative, then you make sure that Ns is less than Nr. How do you achieve Ns is less than Nr? In general, Ns is always greater than Nr. But how do you achieve Ns less than Nr is that by reducing the frequency. That's the logic. So these are the four. So now the four combinations, you see you have four quadrants. So based on that, you go ahead and you will get the multi-quadrant operation. Okay. So then we will solve a simple
Sir,
numerical problem. Yeah, please.
sir, in the above case, when torque
Yeah.
is negative, it's motoring, no, sir, in third quadrant.
Yeah, it's motoring. Did I say it is braking?
No, sir. Uh,
Okay. Yeah, please tell. Yeah, is it visible? The screen is visible?
yeah, sir, it's visible.
Yeah, please tell now. Where is that here now? Yeah, torque is
In the
negative,
case,
speed is. Yeah.
can we say like this, sir? When torque is positive only, it's motoring. When torque is negative, it's all braking. And in the case of third and fourth quadrant, when torque is negative, it's motoring, sir.
See, when torque is negative, see, one thing I will tell you. See here. Uh, yeah, see, someone is continuously rising. Bhan Prakash, I think. Okay. Now you see. Okay. Now you are saying, okay, what you are saying is that if torque is positive, we can say it is motoring, and when torque is negative, we can say it is braking. Are you
Braking.
saying this thing? Are you saying this
Yes.
thing? Yeah,
Yes,
but
sir.
one thing I will tell you that actually motoring condition means, I will tell you, motoring means what do you mean by motoring? Power, power is positive. Am I correct? Can I say like this? Power is positive.
Yes, sir.
So power is positive in the sense, what does that mean?
It's
Uh,
taking power.
yeah, power, yes, correct. We can take taking power. So whenever, not only this motor, okay, any load, you take fan, lamp, or any kind of load, the general convention is that if in that load power is positive, then you can take it as a load. If the power is negative, you can take it as a source. Yes, am I correct?
Yes, sir.
So motoring condition, power is positive. You agree with me?
Yes, sir.
Yeah, okay. Braking condition, power is negative. You agree with me?
Yes, sir.
Okay. So if you agree with these two things, then you see yourself. Now, what is power? You have a formula for the power. I think it is T into omega. Am I correct?
Yes, yes, sir.
Okay. Now you see yourself. So to have power positive, to have power positive, what should be the values of T and omega? Either both are positive or
Eight.
both are negative. Am I correct?
Yes, sir.
So T may be positive or T may be negative. Am I correct or not? So T may be positive, in that case omega should be positive. T may be negative, in that case omega should be negative. Am I correct? So for the motoring condition, you may get positive T or you may get negative T. Yes or no?
Yes, sir.
Similarly, for the braking condition, okay, power should be negative for the braking. In this case, if the power should be negative, then either T is negative or omega is negative. Anyone should be only anyone should be negative. The other should be positive. Am I correct or not?
Yes, sir.
So in this case also, T may be positive or T may be negative. Am I correct or not? If T is positive, then definitely omega should be negative. If T is negative, definitely omega should be positive. Am I correct or not?
Yes.
So now you see that for the braking condition, T may be positive, T may be negative. For the motoring condition, T may be, so you cannot say this thing that the earlier assumption which you have taken, that if T is positive, we can call it as motoring. If T is negative, we can call it as braking. No, it is not correct. Okay. So which parameter you will take as the base is that power you take, not the torque. Okay, power is positive, then only you can take it as motoring. Now whatever may be the T may be negative, T may be positive, we don't need to worry about the torque. We need to worry about the power only. So power is positive, motoring. Power is negative, it is braking. You understood now?
Yes, sir.
Okay, 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 okay. Then we will go and solve this problem. Okay. So I think I did not complete the question yet. So let me complete the question. Then uh, question number two. Calculate the starting torque and current. So that is the question. Calculate the torque and current. Yeah, now we will read the question here, that a star connected squirrel cage induction motor has the following ratings and parameters: 400 volts, 50 Hz, 6 pole, 1500 RPM, R1, R2 dash, X1, X2 dash, everything has given. The motor is controlled by a voltage source inverter at constant V by F ratio. Okay, the inverter allows a frequency of 50 Hz. Calculate the starting torque and induction motor. So how do you find the solution here is that starting torque, we have to find out the starting torque formula. So that you require the equation which we have studied somewhere else. Okay, that we will bring here first of all. Okay, so 3 by omega s Vs square. Vs, see here, see please, Vs in the sense V phase square into R1 plus R2 dash whole square plus X1 plus X2 dash whole square into R2 dash. So this you will find out. Now please here, you don't find out any S here. Slip you don't find out because Because for starting torque, for starting S is equal to 1. I hope you know this thing. So that S is not here. So we made S is equal to 1 already, and I have got this equation. Now please see here now. What else we don't know, what we know? First of all, omega S. How do you find out the omega S? So omega, so angular frequency you have to find out 2 pi n by 60. Okay, then how do you find out n? N can be given as 120 f by p, because omega is the synchronous speed. It's very important. So 120 into, I think the frequency is 50 and it is 6 poles. So it becomes 1000 RPM. Check yourself. It is 1000 RPM. So we got omega s value. Then R1, R2 dash he has given directly in the problem. R1, R2 dash. X1, X2 dash also he has given. Now what is the only thing which you don't know? V phase. So how do you find out the V phase? Now we have to see whether it is a star connection or delta connection. So as it is a star connection, okay, and the line voltage he has given in the problem as 400 volts. Okay, so 400 by root 3, then you will get the phase voltage. So everything you know, then you can substitute directly in the starting torque. So if you substitute directly, you will get the answer. So I don't want to tell the answer now, like please, because okay, I will write the answer here. TST, when you simply when you substitute all these things here, it becomes 51.5 newton meter. Please check yourself whether this is correct or not. Only thing is that you substitute everything you know there. Then next, what he is asking, what is the starting current? So starting current, you recall, just recall that. So current is just voltage by impedance. So voltage is V phase, impedance is square root of R1 plus R2 dash by S whole square, but S is equal to 1 because it is starting current. So whole square plus X1 plus X2 dash. So, so this is your starting current. Voltage by impedance. In the impedance, you make S is equal to 1. So then you substitute everything, 400 by root 3 r1 not everything you substitute, you will get the answer 24.47 ampere. That's it. It's a very simple question. Okay, to understand here. So you remember the equations of all the maximum torque, starting torque, and okay, any other torques are there. So you remember full load torque, rated torque, all these equations. If anyone can remember them, you can easily solve this problem. Okay. So now